Okay, so at this point we are ready to introduce RNNs. And I will start with the definition. So the RNN applies a function to an input sequence to generate an output sequence. But the interesting part is what comes after. So it does that by working on the elements one at a time. So it doesn't work on the full sequence altogether. It goes on the elements in the sequence one at a time, following the order. And that's the first interesting point. Second one is that it has an internal state. And basically, in this internal state, the RNN is trying to capture the relevant information that have been seen so far in the computation. It's okay if it's not completely clear at this point. We will we will go over one example to really understand these two intuitions. Here you also see this image, which is kind of the most common image for RNN. And at this point, you can see that there is an input, which is X, there is an output, which is Y, and the internal state H, which is called H because it's also a hidden state. And maybe the only detail to consider at this point is that you see that there is an index, the index T. And that's because, as we mentioned, the RNN will work on this sequence one element at a time. And this index is telling me which element I'm working on. But let's see one example to make this more clear. So, so first let me introduce the problem for this example. It's a natural language processing problem. It's called name identity recognition. It's actually a very famous problem in this area, but if you haven't heard about it, it's basically this problem of, given some text, I want to attach a label to every word. And this label is telling me if the word is an entity and which kind of entity it is. So in this case, I have only three labels. I have person, location, and this dash label. So the dash label is a special label just to indicate that the word is not an entity. So if I run over this example, you see the input, which is Alan Turing lived in England. And the output is going to be this person. So the first two words, they are a person. So I will attach these labels. The words lived in, they are not an entity. So you see I use the dash label. And the last word is, well, is a location, so I will use the loc label. So here you just see the problem, but now let's see how to use RNN to solve this problem. And here I wrote the definition again, so we can use that. And you see that now, well, nothing happened because I still have to start to run my RNN. What you see is that I have my input sequence, which is this Alan Turing lived in England. And you see that I have this green box on the left, which is the internal state that we mentioned before. And at this point, the internal state doesn't contain any interesting information yet, because we still have to run. So it's just a way to initialize my system, because as you will see from the equations, I need an internal state to start with. So this can be, for example, randomly initialized. So at this point, we start to apply our RNN, and as we said, we want to do that one step at a time, which means we start from step 0, which is the word Alan. And what the RNN does is actually two operations at every time step. The first operation is to compute an updated internal state, so this H0. This is done by following some equations. We will see this equation later on. But the point that is interesting here is that to do this, to create this updated internal state, the input is the current element only, Alan in this case, and also the input is the previous internal state. And that's how we can have the information to flow over these steps. So once the RNN has somehow updated this internal state and created this H0, there is the second operation, which is to produce the output. And the output is a function of just the internal state that we just generated, so only H0. And the idea now is to repeat this again and again for every time step. So let's say now we move to time step 1, so Turing. And you see that we do exactly the same thing. And again, I would like to highlight that the input is just the word Turing and the previous internal state. We don't consider the other words. So just one element at a time. So once I create this internal state H1, we produce the output. And obviously, we go again with these two steps, two operations that we apply. So update internal state, produce the output. Well, in this case, is this particular label that with just a dash. Continue doing that. And let me stop for a second here, because I think this is an interesting case. So here, the RNN is trying to predict the label for the word England. And maybe the RNN doesn't know that England is a location. Maybe it just knows that whatever it's uppercase, it's maybe a name or maybe a location, but it doesn't know which one to pick. And the interesting thing about RNN is that it can leverage on the information built from the past. So the reason why the input is not only the element, but also this internal state, is that hopefully the RNN store in this internal state the relevant information that are needed for the current prediction and for the future predictions. And hopefully the RNN, in this example, stored in this internal state H3 the fact that we saw the word in. And it knows that in comes before a location in general. So by putting together these two information, you see that the RNN has more information to predict the correct output, which in this case is location. So at this point, we know we saw this example, so we know how to unfold, so how to run the RNN over the sequence. We also say that we are unfolding the RNN over the sequence. Let's try to formalize this architecture a little bit more. So we can just introduce the variables that we will use. So we already saw that we will use X for the input sequence, Y for the output sequence, and H for the internal state sequence. In particular, we saw that we have indices because we have various elements, and the index is telling us which one we are talking about. And at this point, we can do yet another step and do this. So we go from this unfolded version on the left to this more generic representation on the right that will help us to introduce the equation. So what I did here is not too complex. Basically, I'm just representing one generic time step t instead of all the sequence. So to give you an example, let's say I focus on the time step 1. Let's say that instead of 1, I use the index t. I came up with this architecture, where the things that may be not clear is this feedback loop here. And this feedback loop is telling us that, like if I go back to the example 1, the internal state will also be used as input for the next step in applying the RNN, so for the next equation. So now that we have this generic representation, we can try to, we can present the equations that govern the RNN. So the first thing is that we said that we have two operations. And in fact, you see two equations here. The first and probably the most important operation that the RNN is doing is creating this updated internal state. So that is ht. And you see that ht is just a function of xt and the previous internal state, so ht minus 1, which is exactly what you see here in this image. Given we are talking about deep learning, we also have parameters. And in this case, the parameters are u, w, and the bias bh at the end. So you see that we do this multiplication, we sum everything together, and we apply a nonlinearity. In this case, the nonlinearity is the hyperbolic tangent, which I will call tan h from now on. And at the end, I end up with this, this internal state ht. So now that the first operation is done, we need to do the second operation, which is to produce the output, so the yt that you see here. And this is similar. So you see that yt is function just, in this case, just of the internal state, so this ht that I just computed in the previous operation. And you see again that we have more parameters. We have v, and we have the bias by. We multiply, we sum, and we apply a nonlinearity that I call g, and that's our output. So the reason why I'm not saying which nonlinearity you are using here is because it depends on the problem. If we stay with the example, the name identity recognition example, in that case it was a classification task, so in that case you would have applied a softmax. But obviously you can apply other nonlinearities like sigmoid and so on. So at this point we introduce these parameters in these two equations. So we introduce u, w, v, and the two biases. And one very interesting point that we need to remember and will influence the way we train this architecture, we need to remember that these parameters, they are shared over time. So maybe it's not clear from this image, but it will be more clear if we unfold the RNN. So if you focus on the part on the right here, you see that again we have the RNN going over the various time steps. And you see that if I focus on the parameter w, it's always the same. So it's w in the first step, it's w in the second step, and so on. So we are using the same parameter again and again. And that's because the recurrent neural network is always applying the same function at every time step. So that means we always use the same parameter at every time step. And we will see this as an impact on training.